which is Michele Visinoni. We can see him there. Okay, please, Michele, if you can try the share screen.
Yes. Okay. Now.
Perfect. Okay. So please, Michele, you can take the stage.
Okay. Thank you. Good morning to everyone. Thank you, Lorenzo, and the organizer for inviting me here in this nice workshop. So today I will present you this work, which is the hybridization of virtual element method for Hellinger-Reissner elasticity problems. And this work is a joint work with Franco Dassi and Carlo Lovadina. This is the outline of the talk. So first of all, we introduce or we recall the problem that we have already seen this morning in the Carlo's talk. Then we give you the motivation behind this work. And then we highlight the main features of the hybridization procedure and the VEM. Here we do not enter into details, but we can see the definition of the local space and the discrete problem. So finally, we will see some numerical results. So the problem is the following that we have already seen this morning. So we study an elasticity problem. So we wanted to study the behavior, the deformation, and the stress of an elastic body, in this case omega, under the influence of applied forces F. In our case, we consider the elasticity formulation, which means that we are looking for two variables, the sigma, the stress, and U, the displacement, such that are verify the equilibrium equation and constitutive law. For this problem, we consider the linear elasticity problem, and the material is homogeneous and isotropic. This is the strong formulation. So the variational formulation of our problem is the following. This is a mixed formulation, and where capital U is the space of the displacement and the capital sigma is the space of the stress, which is the space of symmetric tensor such that they are in each div. For the bilinear form A, B, and the right-hand side, here below we have their definitions. So this is the problem. This morning we have seen some virtual element scheme for this problem, and here today we focus our attention on the low order VEM scheme, in particular the case k equal to 1/2. So the first article, in the first article, the authors designed and implemented this VEM scheme for 2D problems, and here we did the extension to 3D. This morning we have seen a lot of interesting features of this VEM scheme, and one of them is that in this scheme we do not have nodal degrees of freedom, and in particular we do not have nodal stress degrees of freedom. This property is essential in order to apply the hybridization procedure. So the goal of this work is to present the hybridization procedure for this low-order VEM scheme for both 2D and 3D problems. And in numerical, in the section of the numerical results, we will see also the advantages of this procedure with respect to these two standard conforming VEM schemes. So this is the motivation. Now the question is, what is the hybridization procedure? The hybridization procedure was born as only a computational technique for mixed method, which leads to solving symmetric and positive definite linear system instead of the original indefinite one. So in this, the first aim is only a computational technique. And this procedure can be split in two steps. In the first step, we need to introduce a new set of variables, the Lagrange multiplier, in order to impose the continuity constraint of the normal component of the stress. In other words, we wanted to impose the stress HDIV conformity of our problem throughout this new set of variables. In this first step, in this first phase, we the dimension of our linear system increase because we consider discontinuous stress, and also we add a new set of variables. So the second step is essential in order to see the advantages of this procedure. And the second step is we apply the static condensation algorithm. So we exploit the fact that the stress are defined are discontinuous, so we can invert locally invert some matrices, and then we can reduce the dimension of the linear system, and we obtain a symmetric and positive definite linear positive definite one. So this is the first aim of the hybridization procedure. The second aim of this technique, and this we can find in this article, is the following. We can use the information of the Lagrange multipliers in order to reconstruct the solution, the discrete solution, and particularly the discrete solution of displacement throughout post-processing. So here, in this work, we use the idea of a non-conforming VEM. Follows this article. I use Lipnikov-Manzini for vectorial functions. So here we use this non-conforming VEM. So this is the main idea or the main features of the hybridization. Now we move to the space, and we move to the discrete problem. So the spaces, the local spaces for the hybridized scheme are the same of the conforming VEM scheme, the standard VEM scheme that we have seen that we have already seen this morning. So for the displacement, we can use a rigid body motion. So for the displacement, this space is a polynomial space, so it's not virtual, and we use a rigid body motion. For the stress, we use this virtual scheme that we have already seen today, where here we require the traction are in each div, such that they are symmetric, and then we require the normal component of the stress are polynomials defined this way, and the divergence is a rigid body motion. This space is the space of a vectorial function, such that the normal component is a P1, is a linear function, and the tangential component is constant. The divergence can be computed from this information on the boundary throughout the Convergence Theorem. So this scheme, so the local scheme, are the same of the conforming VEM scheme. Now, for the Lagrange multiplier, we need to add this space, so this new set of variables, and here we use only, we define this new set of variables only on the internal edges, where we need the continuity of the normal component. And our choice is the following. We use the same space of the stress, and this is very important. So we use the same space for the stress. And here, in order to impose, to enforce such continuity, we needed to also introduce a discrete bilinear form. So this is the spaces, and so the discrete problem of our method is the following, where here we can see that tau h is a decomposition of omega into polygonal elements, and here this is the global space, and here we can see that we do not require h-div conformity, but we use the Lagrange multiplier, introducing these discrete linear form to impose this continuity. the computation of the bilinear form AH is the same in of the conforming method, and we can use the standard philosophy of VEM, while the bilinear form B and the discrete bilinear form CH can be computed using the degrees of freedom. So these bilinear forms are computed exactly using the degrees of freedom. So this is the discrete scheme. An important feature of the hybridization is that if we choose in a suitable way this space, the discrete solution using the hybridization procedure and the discrete solution of the conforming method are the same. So we can use the same theorem, and this is the Convergence Theorem of how hybridize the problem. So this method is the order of our method is the first order. Today I do not see the convergence results, but I show some other results. And now we move to the numerical results. So for the numerical results, we consider the b-dimensional, we consider both cases. So for 2D problem, we consider omega unit square. This is the solution, and this is the loading term, and the loading term can be computed accordingly from the solution. And for 2D problem, we consider the nearly incompressible material, the case in nearly incompressible material, where lambda is bigger than 1. And these are the 4 meshes that we consider. For 3D, we consider the unit cube. This is the exact solution. This is the loading term. In this case, we consider compressible material. So this is our choice, not so. And these are the 4 meshes that we consider: cube, Voronoi, random polyhedra, and tetrahedra. The first result is about the comparison of the solving time between the 2 methods. So with standard, with the term standard, I refer to the conforming VEM method, and hybrid using the hybridization procedure. In this case, is for 3D problem. The results are for the 3D problems. And so in the first column, in this column, we have the solving time, and these quantities are expressed in seconds. Here, the solving time only on the linear system, and here in this time we have the solving time of the linear system plus other algebraic plus the time of the algebraic manipulation derived by the static condensation. So we can see that we use for the solver we use MAMS for both problem for both method, and here we use a generic solver, and here we use Cholesky because we have a symmetric and positive definite linear system. So that we can see that when we refine the mesh, we can see the hybridized scheme is better than the standard. So is faster, better not, but is faster than the standard. And this for all meshes, for cube, tetrahedra, Voronoi, and random. Another observation is the following in the bracket. Here is the percentage of the time that we spend only for the solving time of symmetric linear system here in the hybrid. So here we have the solving time plus the algebraic manipulation. Here is the percentage of only the solving time with respect to the global time. And this, we can see that this percentage goes to 100%, we can observe the advantages of the hybrid respect to the standard. And this is less than 50%. We can see, for instance, on the tetrahedra, we can see that the standard is better than hybrid. So this is the first result. The second result is about the second aspect of the hybridization procedure, which is the post-processing. So this is the convergence results of the post-processing. Here on the left, we consider the L2 error norm of the displacement of the discrete solution, UH, which is a rigid body motion. So we know the solution, and when we compute exactly this error, and this on the right, we consider the L2 error norm of the reconstruction. This we consider a non-conforming VEM, so we need the projection for to compute this error. These are the results, and we can observe that here for our reconstruction, we gain an order of convergence. So this is the first order, this is the second order, and then the error is less. So this is less than the standard one, the original one. So this is the first results for 2D. We also prove. We also show the semi-norm, broken H1 semi-norm, also for the Howell reconstruction. This the order is equal to 1. And then also we did also for 3D. So here is the post-processing, is for only for the post-processing, is the L2 error norm, and this is the broken semi-norm H1, and the convergence rate respect to the rate that we have from the analysis. That's all. So thank you for